Hello everyone, my name is Srijit Chodiparambil. I am a first year PhD student in Technical University Dresden, and in this talk I will introduce microscopic models for Kitaev's 16-fold way of anyon theories. Here is the outline of my talk. First I will recap Kitaev honeycomb model, then I briefly define what the 16-fold way classification of topological orders is. Then I present the main idea about how to construct microscopic models realizing these topological orders. Then I present the model and its exact solution. Then we characterize the topological order of this model, and we see that they agree with the topological orders of Kitaev's 16-fold way. And let's start. Kitaev honeycomb model is one of the rare models in condensed matter, which is exactly solvable and has anyonic excitations in the ground state, non-abelian anyonic excitations to be precise. So this is the model. It's a 2D honeycomb lattice, and there are three different interactions along three directions from a sublattice. So it's an anisotropic interaction, and if realized in materials, these interactions are inherently different. And Kitaev solved this model using Majorana decomposition, this equation where B and C are Majoranas. And on doing this mapping, this Hamiltonian reduces to this, where UJK is a Hermitian operator which has this form, and its square is +1, which means that you can take only plus and minus 1. And UJK commutes with H tilde, so you can look at a subspace of the Hilbert space where UJK is fixed, and then this Hamiltonian becomes quadratic in C, and it can be exactly solved. UJK are called Z2 gauge fields. And one thing I didn't mention is that when you do this mapping, you're actually increasing the degrees of freedom. And to take control of that, you use this fermion parity constraint, which is obtained from the algebra of the Pauli matrices. So after finding the solution, we have to project it into a space where this constraint is satisfied to get the physical solution. So this is a schematic of the Majorana representation, where the central dot represents this itinerant Majorana fermions, the C fermions, and the dots, the corners, represents BXP or BZ, which are used to form these Z2 gauge fields, which are these links. Kitaev 16-fold. When you solve this Hamiltonian, you see that there exists a gapless space, and Kitaev showed that on adding appropriate weak perturbation, which couples to magnetic field, that there exist non-abelian anyonic excitations, and that the Chern number is plus or minus 1. So Kitaev's 16-fold way is a classification of topological orders of Z2 gauge theory coupled to free or weakly interacting fermions with a spectral Chern number of mu. So Kitaev honeycomb model in this terms is a Z2 gauge theory coupled to itinerant Majorana fermion hopping problem with a spectral Chern number of plus minus 1 when you have this perturbation in the gapless space. So the topological order is classified by nu mod 16 into 16 distinct types, and Kitaev's model realizes mu equal to plus minus 1. In this talk, I will introduce models that will realize all 16 topological orders, and the first one being obviously Kitaev's honeycomb model. The main idea here is to somehow combine Chern numbers and obtain higher Chern number. It's not physically correct, but yes, that's the idea. A useful mathematical tool is Clifford algebra. Clifford algebra of order n has 2n minus 1 gamma matrices which satisfies this algebra. One can also define these gamma ij's, which are useful for defining the Hamiltonian. And it has a Majorana representation, which we borrow from Wu, Rose, and Hong's paper. And in this representation, there are 2n Majorana operators. And when n equal to 2, it's straightforward to see that we get back Pauli matrices and Kitaev's Majorana decomposition. A possible way of achieving mu equal to 2 and 3. For mu equal to 2 and 3, let's look at a higher order Clifford algebra. Kitaev used order 2, we will use order 3. So we have 5 gamma matrices and 6 Majorana fermions. So these 6 different colored dots represent 6 Majorana fermions, and this triangle and this rounded square represents spin at a lattice or a sublattice. Okay, this red links, blue links, green links represents Z2 gauge fields, and you see that there are 3 different itinerant Majorana fermions. And Here we are looking at a square lattice-like model, and you have 4 anisotropic interactions, and you see that there are 2 itinerant Majorana fermions. So if somehow these itinerant Majorana fermions have Chern number 1 each, and they are somehow decoupled, then the total system could have Chern number 2 here and 3 here. So let's see how we get this. So if you look at higher orders of fluid algebra, we again see that for even Chern number or even itinerant Majorana fermions, we need a square lattice, and for odd, we need honeycomb lattice. So this is the square lattice. You have 2 sublattices. The honeycomb lattice, again, the same thing. We'll use honeycomb for odd Chern number and square for even Chern number. So this is our model Hamiltonian using gamma matrices, and it's for Chern number nu. Not getting into the details here, but yes, if you do the Majorana representation or Majorana mapping, you see that there are itinerant Majorana modes coupled to the same Z2 gauge field, and it's static in the sense that it commutes with H tilde. And if you look at a subspace where Uij is fixed, then these itinerant modes decouple. And the ground state flux configuration can be obtained from the Leib's result, where honeycomb has a 0 flux space and square lattice has a pi flux space, from which you know what the values of Uij are. We can even study the ground state. So this is the phase diagram, square lattice, and this is the phase diagram of the honeycomb lattice. And you see that there exists a gapless space in each case, and in our paper we show that we can find a perturbation which, when added to the Hamiltonian in this space, achieves a Chern number of 1 for both square and honeycomb lattice. The form of this perturbation is straightforward for honeycomb. For square lattice, it can be developed analytically. Okay, let's go fast. Characterizing topological order. So we have models which have itinerant Majorana modes of Chern number 1, and the total Chern number would be equal to the number of itinerant Majorana modes, which is mu. And yes, so we have all possible Chern number models. So let's check if they have edge states and topological spin of anyons to characterize the topological order. So we're looking at a cylinder now, and it has periodic boundary condition along one direction, open boundary condition along the other direction. We solve the Hamiltonian, and we see that for each itinerant Majorana fermion, there exists a pair of gapless Majorana edge mode, as you can see from this dispersion relation. Thus, for a new Chern number model, you have exactly new pairs of gapless Majorana edge modes. And using some CFT argument, one can show that the anyon topological spin of this model would be mu pi by 8. And this agrees with the Kitaev 16-fold recharacterization. Another interesting thing is the topological ground state degeneracy on torus. So now this is a torus. Torus has 2 loops, one along this direction, blue, and this. So one can define loop operators, which I didn't get into because of the time. But these loop operators has eigenvalues +1 or -1 each. So you have 4 possible configurations, and it can be shown that in these 4 possible situations, the ground state has the same energy in the thermodynamic limit. So the ground state degeneracy is 4. For even Chern number models, it's 4. For odd Chern number models, however, it's 3, because one of these states, which has eigenvalue +1, doesn't satisfy the local fermion parity constraint. Okay, so there is topological order, which is in agreement with Kitaev's 16-fold way classification, and thus we have constructed microscopic models for each of the 16 distinct topological orders in Kitaev's 16-fold way, and we characterize this order by calculating the anyonic, topological spin, and topological ground state degeneracy in each case. And this agrees with what Kitaev predicted in his classification. And for nu equal to 2, 3, an appropriate representation of a model was chosen for square and honeycomb lattice, and they have a close similarity to Kugelkomsky type models for transition metal oxides, bringing our model to the materials side. So I'd like to thank the collaborators, Dr. Urban, Professor Vojta, Dr. Lucas, and my supervisor, Dr. Hong Hao. Thank you very much.